Hi ladies and gentlemen, we're going to take a look at a couple of example problems just to give you a flavor for how we can use the composition of functions. So start with this example, which is straightforward. We have f of x is equal to e raised to the x, and we have g of x is equal to x cubed. And the first thing we want to calculate is f of g of x. And as we discussed previously, that's going to take x and map it over to g of x, and then use g of x and map it as the input into the f function and give us f of g of x. So following this, we just have x, which is mapped to x cubed via the g function, and then we're going to take an x cubed and put it in for the x's in f, and that's going to give us e to the x cubed. So f composed with g with an input of x is equal to e to the x cubed. We're also interested, for practice sake, in reversing this and taking g and composing it with f. So the idea is exactly the same, except now x is going to be mapped first to f, and then we're going to take the f of x, and that is going to be the input into the g function. So we have g of f of x. Again, we just follow along. X is going to be mapped to e to the x, and then we're going to take that e to the x and put it in as the input here in the g function, and that's going to end up being mapped to e to the x quantity cubed. So g composed with f, where x is the initial input, is equal to e to the x quantity cubed, and of course we can simplify. This is equal to e to the 3x. That's just an example. The next example I want to do is from the textbook. It's on page 254, and it's problem number 94. This is not one of the assigned homework problems, but it provides a really nice problem for us to be able to jump into. Go ahead and pause the video and just read through the problem. All right, so now that you've had an opportunity to read it, there are really two key pieces of information. One of them is we have this forest fire and it is expanding in a circular pattern. So we need to recall or derive, you don't have to have this on the top of your head, but the area for a circle is equal to pi times the radius squared. So this is one of our functions, and using the function notation, we really want to write this as a, which is a function of the radius, because the area is a function of the radius. As the radius changes, the area changes. And this is equal to pi r squared. So you don't see it this way often, but this is really what's happening. We have area as a function of radius. Secondly, the problem tells us that the radius is a function of time. As time increases, the radius of this circle is increasing. So we have radius as a function of time, which is equal to 2t plus 1. And now what we're interested in really is finding the area as a function of time. So we're going to have area, which is a function of r, but that r is a function of t, and now we have composition of functions. We're going to start with a t value. We're going to map that t value via the r function to r of t, and then we're going to map that over to the area, and we're going to end up with the area as a function of r of t. So let's do it. T is mapped over to 2t plus 1, and then that becomes the input right here for our area function, and we're going to take that value, we're going to put it in here, which means we're going to square it, and we end up with pi times 2t plus 1 quantity squared. So this is the expression for a composed with r as a function of t, and it's equal to pi times 2t plus 1 quantity squared. And this allows us to be able to do the kinds of calculations that you'll see in calculus when you move forward, where we look for rates of change. What is the rate of change of area as a function of time? And these are the types of questions that people are asking all the time, right? How much manpower do we need to be able to combat this fire? Well, in large part, that's a function of how quickly it is growing. How much area is it increasing by every hour? And having a representation of area as a function of time allows us to answer that question directly. Thanks again. Good luck with the rest of the homework.